Okay, so kinetics and the gas laws. So if you got your paper out in front of you, we're going to take a few minutes to do some research on something that happened with gases that happened in our community. There were 2 young children that were killed with phosphine gas. It's been about 3-4 years, something like that. Could this have been avoided? Okay. Has anything like this happened before? These are some of the questions I want you to research and get to. So we're going to take 15 minutes. You're going to do this with your partner. You're going to research as fast as you can. You've got these 4 questions, plus you've got one in the center. What is your takeaway? In other words, after you do all the research, what is one thing you take away from this? So I want you to grab either computers or your phones. Get going, research. You have 15 minutes, and I'm starting that right now. Okay, let's come back together. Let's talk about this. How does fumitoxin work? What is it used for?
Okay, so fumitoxin is like a pesticide that kills like rodents and stuff, either on like grain, plants, or just at homes. You bury it in the ground, and the moisture from the ground will react to that fumitoxin and make phosphine gas, which
Okay, so that leads into the next question. What is phosphine gas and what does it do? Somebody else. What is phosphine gas? It's a gas. What is it made of? It's phosphorus and hydrogen. It's pH 3. Notice what family it's in. Okay, our nasty family, right? Nitrogen, explosion, arsenic, antimony, things that are poisonous. Okay, what does it do? Okay, does it just cause irritation or does it do something more? Stops the cells from doing their jobs. Basically a neurotoxin, right? So it shuts down the nerves and things stop working. Okay, so why the 2 youngest and not the older children and the parents? Why those 2 died? Good. And they're also, if you think about it, babies and toddlers are where? Where do they usually have? On the ground. They're usually on the ground. And that's where the heavy gas was. That's where the phosphine gas was. So what were some of the symptoms? What made them, what did the parents think they had? The flu or food poisoning, right? Because it looked like that. Mom did take the kids to the doctor, right? And the first time the doctor said what? They got the flu. Take them home. Next time they came back, baby was not doing too well. Baby actually was doing very bad. In fact, they sent him down to primary children's. And they finally figured out what was going on, but by then it was too late. And then the 2-year-old followed soon after. So this is a sad story. It's not just a story. Did you notice anything when you were researching? Did this happen before? Yeah, it's happened a lot of different places. So whose fault is it? Guess what? If you're the landowner, it's your fault. Why? They had the decision to do it or not. So you guys are almost adults now, right? And so you're going to be in charge of a house pretty soon. So if you hire somebody to come get rid of, what were they called? Voles. So they're like little rats or little mice or big mice. If you hire somebody to come take care of it, you better be asking a lot more questions. What are you using? How toxic is it? And you might not just want to take their word for it. We took, 10 minutes? And what did we find in 10 minutes? Lots of information. So if the parents had just put in fumitoxin into a search, what do you think they'd found out? It says toxin. It says toxin. Okay, so as a responsible citizen, you guys are now going to be having a lot more weight on your shoulders. Okay, it wasn't just the exterminator's problem, but it was the exterminator's problem, but it was the people that hired the exterminator's problem. And so that's why it's been in the court systems going back and forth for a long time, because not all the responsibility was on the exterminator. It was on the parents for hiring them too. So as we go through this, a lot of what we're going to be talking about in this unit has to do with what you're going to have to deal with when you get to be an adult. Okay? You cannot always trust everybody on their word for what they say. Oh, this will kill the voles. Oh, by the way, it will kill your kids too. You know, they didn't say that, but, you know, that did happen. So you need to be responsible. Why was it in the yard? We decided it was in the yard for what? Kill the voles, because mom and dad hated those little tunnels that are everywhere in the yard. Okay, how did they clean it up? Water. Okay, so they turned up the yard and then they flooded it. But what did they do in the neighborhood? They evacuated it. They evacuated, had full hazmat suits on, and they had fans. Fans? Why would they use fans? To disperse it, because it was down in a little hollow, and if they would have just let all the fumitoxin react, it had all this phosphine gas in it, where would it have landed? In that little hollow. And so they needed to have the fans to blow it out of the hollow and disperse it, because in small amounts, phosphine gas doesn't hurt you, but in larger amounts it does. So they had to disperse it. That was the only way to get rid of it. Yes? It could affect pets, yep. It could affect pets. A 4-year-old and a 2 baby, you know, but the cat, no big deal. Okay, so there is some responsibility that we need to worry about here. So let's go ahead and start into the unit. So we have some observed properties. 2 elements. These are some stuff that we've already done, but also falls into this unit. You will notice that a lot of the units that we've done in the past will come back to haunt you. You can't just do them and forget them. Some of you said that about the family test, like protons, neutrons, and electrons. I don't know. We might need to know those. Okay? All right, so what 2 elements are liquid at room temperature? Mercury and bromine. So bromine is a dark red liquid, and mercury is a silvery liquid, right? Okay, what are the elements that are gas at room temperature? Noble gases would be part of them. What else? Hydrogen is. What else? Oxygen, nitrogen. Nope. Fluorine and chlorine. So the ones in yellow are gases. The ones in blue are liquids. What is everything else in white? Solids. Okay, so most of the periodic table is solid. So if you know what the 2 liquids are and what the gases are, you know everything else is solid at room temperature. So we've got NOF again, nitrogen, oxygen, fluorine, and chlorine, and hydrogen besides the noble gases. Okay, those are our liquids. And then the last question, I forget what the last question was there. What is the most common state of the elements found? We just said that. It's solid. Okay, and that's what we're going into right now. So the first property we're going to talk about is density. In a solid, density is high. In a liquid, it's high, but usually a little bit lower than the solid. Okay? And gases have very low density because they are spread far apart. The next property that we're going to talk about is shape. A solid has a definite shape. Okay? We know exactly what it looks like. A liquid has an indefinite shape, but it takes the shape of whatever container it's put into. Okay, so it takes the shape of whatever container it's put into. A gas will take the shape of the container plus whatever is filling around the container unless you put a lid on it, and that will fill the whole space. Where a liquid will only fill up the space that it fills. A gas will fill the whole space. Compressibility, how well can I compress something? Force it to be smaller. A solid, not much. Okay, I might be able to squish it down a little bit, but not much. A liquid is also usually small. If that weren't true, my brakes on my car wouldn't work, right? Because we use brake fluid, and the brake fluid, when pushed, pushes calipers together to stop us. If that liquid compressed, then the calipers would never close and we would never be able to brake. So when we have air in our brake lines, then the calipers don't close and we have problems. So that's an important thing when we're doing brake line, that we bleed it so it doesn't have any air in it. Okay? Gases can be compressed a lot. Thermal expansion, that's how does it react with heat? Does it expand? Does it compress? So a solid doesn't move very much. It might move a little bit, but not very much. Okay, a liquid is also small, but not as small as a solid. So it will expand a little bit more or compress a little bit more. And a gas will speed up really fast and fill more space, or if we cool it down, it will take a lot less space. And the only thing that is different here is with water. Water will, with thermal expansion, even go farther. And when I take heat out of it, it actually, when it goes from a liquid to a solid, it actually expands, which is opposite most things. Okay, so we're going to work with the density equation. How many remember what the density equation is? Mass divided by volume. Remember your dense if you're in love, right? Okay, mass divided by volume. So as we look at this, we do a simple one where we have mass here, we have density here. I want to solve, this is a little bit of review, yeah. I want to solve for volume. So because of that, I'm going to switch these two places. In other words, I'm going to times both sides by volume, divide both sides by density, and I will get volume is equal to mass divided by density. Okay, throw it in. We are going to use calculators, so if you've got a calculator, get it out now. We're going to be working with them a lot. Grams divided by 1.03 grams per milliliter. So grams go out, we're going to be left with milliliters. What's my answer to 3 sig figs? Calculator. What? 115. Calculator. It's another word for calculator. You got 121? You got 21? 121? Okay. 121. It's okay. It's all good. Okay, so on this next one, we've got a little bit more going on here now. Copper metal has a density of this at this temperature. And it has a density of this at this temperature. And I need to calculate the change in volume that occurs with, by the way, this is supposed to be grams, when a 10-gram piece of copper is heated from 20 to 100 degrees. So I want to find the volume, so I'm going to use the equation we did above, but I'm going to have to do it twice because they have two different densities. So I'm going to do it for the volume at 20 degrees is going to be 10.0 grams divided by my 8.92 grams per centimeter cubed, and I'll get centimeters cubed. And my volume at 100 degrees is going to be 10.0 grams divided by 8.83 grams per centimeter cubed. Grams will go out again, and we'll end up with centimeters cubed. Go ahead and give it to me in 4 significant figures. Yes? I changed the centimeters cubed to grams. It was supposed to be grams. Okay, what do we get on the top one? 4 significant figures, because we're going to do some stuff with it. 1.121. Okay, what's the second one? Anybody got it? 4 sig figs? 1.132. 33. Okay. So to take the difference, all I'm going to do is take 1.133 minus 1.121, and I get 210, right? And that's centimeters cubed. By doing that and carrying a little bit extra to start with, I still am short by 1 significant figure because I only have 2 here, but that's okay. So I know I'm going to change by that much. Okay, I'm going to change by that much. So I've actually grown that much by heating it up in volume. Okay? Okay, are we okay with this? It's basically just the density equation. We just do it twice and subtract them. Get the difference. So they could have put in here, instead of this, they could have said, what is the thermal expansion difference? Okay, so they could have said that instead of the way I put it. All right, so we're going to go on to the kinetic theory. I'm going to give you the kinetic theory the way it is stated, and then I'm going to give it to you an easier way. So don't write it down the first time. Wait until I give it to you the easier way, but I'm going to give it to you in the words that it's given. And I'm going to give you an easy way to remember at the end, okay? So kinetic theory basically is, how does gases move? How do they collide? Do they collide with each other? How do they collide with the wall? How do the pressures affect everything? Okay? How does bromine hang around? Remember, we have our diatomics, our twins, that hang around in pairs. When they're in gas, they still hang around in pairs. Remember, phosphorus and sulfur are also, P.S. by the way, phosphorus hangs around in 4s, sulfur hangs around in 8s. Okay, so they will still hang around. Everybody else is by themselves. Okay, so if I have helium, it's just going to be by helium. If I have beryllium as a gas, for some reason, it's just going to be Be. Okay? All right, so here's the postulates, the actual postulates of the kinetic theory. Number 1, gases consist of tiny particles, atoms or molecules. Number 2, these particles are so small compared to the distances between them that the volume or size of the individual particles can be assumed to be negligible or 0. 3, the particles are in constant random motion colliding with the walls of the container. These collisions with the walls cause the pressure exerted by the gas. Number 4, particles are assumed to not attract or repel each other. Number 5, the average kinetic energy of the gaseous particles are directly proportional to the Kelvin temperature outside. Great, wonderful. Okay, I'm going to give you a short version. I call it the toddler rules because toddlers are considered 5 or under, right? There are 5 rules. Okay, so here we go. Number 1, particles in an ideal gas. So this is all talking about ideal. Okay, and everybody thinks little babies are so cute, blah, 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 whatever. Okay, number 1, they have no volume. Basically, I don't have to pay for them when I go somewhere because they can sit on my lap. Okay, so they have no volume. Number 2, they have elastic collisions. You ever watched a toddler trying to learn how to walk? As long as nobody's looking, if they fall down, what happens next? They get up. But if you're looking, what happens? Oh! They're crying because they look at your face and say, what should I do? And your face goes, and then they cry. So if as long as you're not looking, they have elastic collisions, so they keep going. Okay? Number 3, they are in constant, random, straight line motion. If you've ever watched a toddler, they get an attention on something. Oh, Mama's glass. And Mama takes it away and, oh. And then they, oh, and go to something else. But it's straight line motion. They're going for whatever they see that has attracted them, and it's random. It could be, oh, I like your hat, kind of thing. And we're going, okay, where did that come from, right? Okay, 4th one, they don't attract or repel each other. So if you've ever put a group of toddlers together, they just play. They don't really care. I'm going to tell you a story about when my kids were younger. Don't be offended, but this sort of does sort of what the non-attract or repel. So they were sort of sheltered, I'll say sheltered. Okay, they'd never seen a black person. Okay, and the first time I went to the store with them, my daughter looks at a black lady that was standing next to us and says in a very loud voice, "Mommy, how come she didn't take a bath?" Ah, yeah. So she wasn't attracted or repelled by it. She just wanted to know why she was darker than any others. And so we had to go through that explanation of some people have different color skin and it's okay. Well, a little while later, same daughter, we were in the store and there was a guy that was really tattooed out and had some rings and things and, you know, she goes up to him, not scared at all about him, and I'm like, oh, you know, sort of scary. And she walked right up to him and says, "Didn't your mommy tell you never write on yourself?" Oh. Like, oh, geez, okay. They were really cute with him, and they were really cute, and it was good, but I was horrified. I was absolutely horrified. She was not attracted or repelled by anything. right? She's a little sassy one. Yes, she is. She still is. So they're not attracted or repelled, right? They see things for what it is. Hi, how are you? Like my grandson, my husband doesn't have hair on the top. And he just realized it. And he says, what did you do with your hair? Did you put it in a drawer? And my husband says, no, it just went away. Can I have some of yours? And he says, yeah. So he grabs some, put on his hair. And he went, look, I see that one. So they just don't know social norms. They don't know that kind of thing. There's no attracting or repelling. Everybody's okay, right? Okay, and the last one, number 5. They have an average kinetic energy, or average energy, related to the Kelvin temperature outside. If it's warm, they want to go outside and they want to play at the park. I want to go down a slide. I want to play in the sand. But if it's cold outside, they might go outside for a little bit, then they'll come in, I want my blankie to snuggle, right? So they don't move very much when it's cold outside. They want to just snuggle. So this is how I remember it. These are the 5 toddler rules. Okay, toddler, ideal gas, 5 rules. Okay, this is how I remember it. I had to make it in my head because that other stuff, that postulate stuff, before it didn't make sense. Okay, you got the 5 rules? Okay, without looking down, who can tell them? They have no volume. 1. Straight line random motion. Yes. Number 2. Elastic collisions. Number 3. Don't repel or attract. Number 4. What's the last one? Energy is related to the temperature outside. Woohoo! So you really quickly can relate it to the under 5 toddler rules. That's ideal. Okay, got it? Okay, but get real. Teenage rules, how are you different? Particles in a real gas are, how are they different? How are you different from toddlers? You have to pay, so you take up space, right? You take up your own volume. Okay, how else? There's actually 3 here. It says 2, but there's actually 3. Okay, have your own volume. What else? Yeah, you're attracted and repel each other, right? Because some people you just don't like now, and some people you're like, ooh, la la. Right? Okay, what do you think the next one is? You don't know. You have learned through driver's ed, collisions are not elastic, right? Once you crash on something, it is going to be bent, and collisions are not elastic. So those are the 3 things that you're different. Now, every mother wants their teenager to go back to be ideal again. So how can I get real back to ideal? What things can I do to make them ideal? When are teenagers ideal? You're not ever? Say it again. Not in school. When are you not in school? Summer. So gases behave most ideal when you're at low pressure because you don't have to worry about tests and about quizzes and about whatever. So low pressure, high temperature, because that's summer, right? And what else do you think? There's one more. I hate this class because she always does a seating chart and she always sets me next to. Okay, I can choose who I want to hang with in the summer, right? Sorry, I used old vernacular. I can choose who I am with in the summer. So it's a non-polar situation. I don't have to sit next to that person I really don't like, or next to that person I really, really, really like. Okay? All right, so let's see if you can remember without looking down. Okay, get real. How am I different? I take up space. No elastic collisions and attract and repel. Okay, that's 3. There are 3 things I do that make me more ideal. What are they? Low pressure.
High temperature.
High temperature. Non-polar situation. I can choose who I'm hanging with. Okay, so here we go. We're going to define these. Kinetic energy. This is the energy of motion. This is the energy of motion. When I have energy of motion, I have an equation. Kinetic energy is equal to 1/2 mass times velocity squared. That is not volume. That is velocity. Lower v is velocity. So I can find out the amount of energy I have by timesing 1/2 times the mass times my velocity. Potential energy. Again, just like having potential to do well in this class, potential energy is just the energy that's stored. It's a attractive or repulsive force acting on it. So it's a stored energy. Okay, it's a stored energy. Cohesive forces are related to potential energy. Okay, these are the attractive forces between particles. It's held in place. So it's sort of held together. Disruptive forces have to do with kinetic energy, and these are the forces that result from particle motion. So it's so associated with how fast or how well I'm doing something. Okay, but it is related to kinetic energy. So we've got two things that sort of go together, kinetic energy and disruptive forces, and potential energy and cohesive forces. We're going to do some problems with these and talk about how they affect what's going on. I'll wait until that bob and weave goes down a little bit, so I know you guys are mostly done. Well, the bob and weave from the back, trying to see around, and then up and down from the front. Yeah, the bob and weave. Okay, looks like most of you are done. Don't move, don't go. Okay, going forward. All right, so what is the equation for kinetic energy? Let's see how well you remembered it.
Mass times velocity.
Velocity squared. So what in that equation has the most effect? Mass or velocity? Velocity. Okay, so let's look at this picture. This is one picture that you have. So I have a toy ball. I throw it straight up in the air, and it comes straight back down to where it is. Let's talk about each part of it. This part right here is what?
That's gaining potential and losing kinetic.
This is what we call kinetic energy. It's energy of motion, which is the disruptive forces. Okay? When I get to the very top and that ball is sort of hanging there before it comes back down, what do I have there?
Potential.
Right at the top, I have potential energy, which is my cohesive forces. Okay? Then I'm coming back down. What's happening? More kinetic energy with disruptive forces. Okay? So I'm sort of looking at things right here really quickly. We okay with that? I'm not going to write anything else. I'm just going to talk about what's happening. Okay, now on the next one, it has a football thing here. So I'm going to say that this is my 180-pound dude, which is actually 81.8 kilograms, and he's going 8.0 miles per second that way. Okay? This guy, I know he should be a little bit fatter. We'll make him a little fatter. He's a 260-pound, 118.2 kilogram, but he's only going this way 3.0 meters per second. And
I thought it was miles per second per minute. I was like, whoa!
Meters per second. So I want to know which one's going to be pushed back and which one has the most kinetic energy. So let's do one at a time. So let's do our 180-pound dude first. Okay, so remember kinetic energy is equal to 1/2 mass times velocity squared. We want to use the kilograms. So 1/2, and the mass was 81.8 kilograms, times by velocity, which is 8.0 meters per second, but that's squared. Now, kilogram meters squared per second squared, that unit is what we call a joule. So if you want to write that down, a kilogram meters squared per second squared is called a joule, and that's an amount of energy. So if we do that really quick, 8 squared is 64. 64 times 81.8, and then divide it by 2. Somebody do that. I'm not going to do that part in my head.
I did the 260-pound one. The 260.
Oh, well, let's do this one first, because I don't. Okay. So 8 squared is 64. So 64 times 81.8, then divide it by 2. What do we get? I'm just keeping track of which one it is. This is my 180-pound guy.
I got a really big number.
Okay, what'd you get?
107,000. I don't think that's right. That's why I was like, hold on a second.
Okay, so 60, 2617, anybody else got that?
26, yeah, 26.
Okay, so we'll do that. Then we're going to take the other guy, the 260-pound dude, and we're going to do the same thing with him. So the kinetic energy is going to equal 1/2 times 118.2 kilograms, and we're going to take 3.0 meters per second squared. So 3 squared is 9. 9 times 118.2, and then divide it by 2. 530.
No, I thought it was 50.
I'm hearing, what is it? 531 joules. Ooh, look at that. Look at the difference in that. That's almost 2,100 and something joules, about, okay? So it's got something like that. So which one's going to push back? This guy's going to push this guy back, right? Even though the other guy's bigger. The reason why? He has more velocity coming at him. Okay, he has a higher velocity. The other one didn't have enough speed going up, so when he hits it, he's actually going to push him back. Even though he's lighter, velocity is actually stronger than the mass. Okay? As long as it's not too out of proportion. I mean, if you had a 30-pound person versus a 230, yeah, that's going to have some problems. Okay? This one is basically, that's just basically 200, that minus 531. I said it was about 2,100, about. Okay, I'm off a little bit because it's probably 2,000 something. Yeah, give me the exact. We'll put the exact in here. It'll be 20 something, but it. 86. Thank you. Okay, about 2,100. Okay, so going forward. Now we're going to not be working with actual numbers. We got to sort of think this through. Okay, so the greater kinetic energy, hydrogen molecules. Hydrogen molecules are H2, right? So the mass would equal 2 times 1.008, right? Which would be 2.016 grams. Everybody okay with that? Okay, now keep going. Traveling at a velocity, so velocity here is 2v. It's something I don't know. It's 2 times the velocity of something else. Helium molecules over here, helium is just helium. And the mass of helium is 4.0 something, 026 grams. And it says it's traveling at a velocity of v, so v is just v. Which would have the greater kinetic energy? Oh, I know how to do kinetic energy. Kinetic energy is 1/2 mass times velocity squared. So plugging in 1/2 2.016 grams times velocity squared. Everybody okay with that?
Yeah.
Okay, so this one, somebody do the thing. It's going to be something v. Over here, we're going to do the same thing. Kinetic energy equals 1/2 mass velocity squared. 1/2 mass 4.0026 grams times v squared. So this is going to just end up being 2.0013 v squared. I can do that one in my head. Okay, what's this other one? Sorry, v squared, yep. So 4 times 2.016 and divided by 2. 4.032, yep. Okay, if you do this, this will be 4. 4 into 2 will leave me a 2. 2 times that is that. Okay, so which one is bigger velocity? Well, I can take and I can cancel out v squared, right? So it's 4 to 2. This is faster. Right? Get that? All we did was do the kinetics again, find out the kinetic energy. We got down to the kinetic energy. We want to know which one was going, which would have the greater kinetic energy, and it would be this one. Okay? Because velocity was twice as big. Right? Okay, so going forward, we've talked about states of matter since you were probably in 2nd grade. What's a solid? What's a liquid? What's a gas? You've known. But we're going to add one. It's plasma. What is plasma? Plasma is just what? Superheated gas that has a charge. Okay, it's got to have a charge. Okay, so plasma is superheated, but it has a charge. Okay? The next state. Yes? Why don't they ever talk about what? We do when you get up into upper physics and upper chem. Okay? All right, so let's go through these. Let's see what you can tell me about this. Explain why each of the following observations using kinetic molecular theory are 5 toddler rules. Okay? Remember our 5 toddler rules? You're going to explain these to me using the 5 toddler rules. So now, letter A, gases have low density. Which of the 5 toddler rules? Have no volume. Good. Okay, a gas always exerts uniform pressure on all its walls in its container. Which of the 5?
No straight line being tracked.
Say it louder.
Constant random straight line.
Constant random straight line motion. So you've got to think of it, if I had a tennis ball in here and I threw it at that wall, that it would have the same energy coming off, so it would also be elastic, right? Collisions are elastic. Same energy coming off, it would hit another wall and keep going back and forth and back and forth. So that's how the pressure would be uniform, okay? Solids, liquids, and gases all expand when heated.
Thermal expansion.
5 toddler rules, which one? Number 5, what was number 5? Average kinetic energy increases with temperature, yep. Okay, so going forward, so this is sort of giving you more pictures to see pretty. Okay, so now we're going to talk about them right here. The following statements are best associated with solid, liquid, or gaseous states of matter. Match the statement to the appropriate state of matter. Temperature changes influence of volume of this state substantially. Which one? I'm going to have you do solid, liquid, or gas. Solid, liquid, or gas. These are sign language S, L, and G. Okay? So which one? Solid, liquid, or gas? Tell me with your fingers. If you chose gas, whoops, you didn't see that one. Gas, you're right. Okay, in this state, constituent particles are less free to move about. This one's actually wrong when it was put up. So they're not allowed to move around. Solid, liquid, or gas? Solid. This one should be solid. So as we're looking at that, that's wrong. That should be solid. Okay, next one. You can see I did a copy paste and forgot to go back and fix. Pressure changes influence the volume of the state more than any of the other 2 states. It is gas. Okay, sideways or G. Okay, this state is characterized by an indefinite shape and a very low density. Low density. That's the key. It's a gas. Okay, we didn't do any liquid, no. Okay, so let's talk about some characteristics of gases. Gases will expand to fill any container they are in. They have random motion, no attraction. Yeah, this is just extra. This is just review. Gases are fluids like liquids. They will flow. So when they talk about gas flow, there is still like liquids. They have no attraction because they're so far apart. It's really hard to have attraction with somebody, say, in Idaho that you really like. It's really hard to have that attraction when they're that far away. Okay? Oh, okay, let's go to New York. That'll be worse. Okay? Gases have very low density, no volume, lots of empty space. So, some other characteristics, they can be compressed. No volume, lots of empty space, so I can compress them. Gases undergo diffusion and effusion, and you need to know the difference. Diffusion is if I have something I sprayed in the room over here and it diffuses throughout the room. Effusion is when I have just a small pinprick hole and it's coming through that, or it effuses through a hole. So if I want to know about a gas leak, I'm going to put a sulfur compound in natural gas so that when it sneaks through a small hole, I can smell it. Okay? Because it will effuse through the hole and diffuse through the room. Does that make sense? Okay? So we do need to know the difference between diffusion and effusion. I'm going to get back to your notes here in just a sec. But those are two things you do need to know the difference of. Okay? And they do that because of the random motion. Random straight line motion. Okay, so let's talk about pressure for a minute. Pressure is a force over a given area, right? Okay, so what causes pressure? Well, if you have a gas particle in a wall container and they crush into each other, you have pressure, right? As we look at pressure, these things right here are what you need. So define pressure. Pressure is what? Force over area. What are these numbers? These numbers are very, very important to you. Write them down. Make sure they put it in the right place. So 1 atmosphere is equal to 760 torr is equal to 760 millimeters mercury. By the way, the guy that did with millimeters mercury, his name was Torr. That's why these two are the same. Okay? 101.3 kilopascals, 29.92 inches mercury, 14.7 psi pressure per square inch, and 1.0313 bar. You'll notice that bar and kilopascals are off by 100, right? So they're related. It's going to be our conversion. So if we want to go from one to another, this is where we can set up conversion factors. Okay? I mean dimensional analysis, yep. Okay, so we're going to do some dimensional analysis right now. I'm going to set up the first two for you, and you're going to do the rest. So here we have a weather report, and it says that it's 28.6 inches mercury. I don't want it in inches. I want it in something else. Okay, watch. Start with what you're given, 28.6 inches mercury. You're going to set up a factor label. You're only going to do one conversion. What do you want to get rid of? Inches mercury. So that goes on the bottom, 29.92 inches mercury. What do you want to go to? Atmospheres. So that goes on top, 1 atm. Then you can cancel out inches mercury, and you got your answer. Okay, torr, the same thing. You start with what you're given, 28.6 inches mercury. I want to get rid of that, so the 29.92 goes on the bottom. This time, though, I want to go to torr. So torr is right here. So I'm going to put 760 torr on the top. Inches mercury will cancel. Has anybody got the answer for the top one? It should be point something, right? 0.9558. So we're going to do, 0.956 atm because we had 3 sig figs. Okay, anybody got an answer for the second one?
Oh, So we need to go from insulin to the
Somebody do the next one real quick. It should be just less than 760, right? Should be just less. 726. Now, this is important. Torr is the same thing as millimeters mercury, so I can really quickly put millimeters mercury right here. Okay? I'm sort of doing them up a little bit because I know the back row has a hard time seeing. So when we do PSI, we would divide by the 29.92 and we would times by 14.7. Good. When we do bars, we would divide by 29.92 and we would times by, what's bar? 1.013. To get KPA, I would divide by 29 and I would times by 101.3. Okay, so I want you to finish that. We're going to start here next time, actually on the next slide. Those of you that got a calc computer, make sure you put it away. We are going to do lab next time. Listen, please. We are going to be working with full-strength ammonium hydroxide, and we're going to be working with full-strength hydrochloric acid. So, wear something, yeah, that you don't necessarily like. Those of you that have contacts, you need to be really, really careful with this lab. So it needs to be the full goggle for you. Okay, not the Vice Gogs. If you don't have contacts, you're okay. It's just that the ammonia, even though we're going to be working with it in the hood, tends to love to stick to contacts. And then it'll be bad.
I really forgot all this stuff. I had some other comparisons to I'm so upset, but it's so useful.
Yep, you're going to get them again. Okay, have a great day.